Okay, let's learn a little bit about populations. So a geographic range is where the population is actually located. It might be a bunch of trees, it might be a group of deer, or it might be people. So this picture is of a sugar maple, and here is the geographic range. You can see they are in the upper northeast of the United States, all the way over to Minnesota. We have sugar maples here, and down towards Tennessee and Kentucky, and back up. Sugar maples are what actually makes maple syrup for us. Okay, so density means the number of individuals per unit of area. So in this picture, we've got quite a dense population of penguins. Okay, so the distribution of the population, it could be considered uniform, which is on the left. That means they're equally distributed amongst the area. You can see they've got a little distance between each one. There is a random distribution, and that's where you can see a little bit here, some there, and then there's a big space, and one. It's just random. And then there's a clumped variety. The clump distribution means that they're all kind of together, okay? Just like these elephants, they kind of roam the area in a big group. The human population in the United States looks like this. Can you tell where there is very few humans in the population living in areas? Okay, so if you look over here towards the Midwest, there's just not a lot of people in there. You can see here it means it's one or less than one person per square mile when it's colored like this. So Alaska has less than one person per square mile in most of that state. There are not a lot of people that live there. The most amount of people probably live right in Anchorage, and then there's a very dense population up here in Fairbanks. Minneapolis is right here. So if we look at how many people per square mile, it looks like maybe 71, a little less than around 70,000 per square mile in the Minneapolis area. Could be true. And it could be down to as small as 2,000 to 3,000 per square mile in that same area. Now, I did read in another map that 2 out of 3 people live within 100 miles of the border of the United States. 2 out of 3 people live within 100 miles of the border. That's kind of a big number there. Okay, let's keep going. Okay, so growth rate is the number of individuals that are either going up, down, or staying the same. So the growth rate can go up, the growth rate can go down, or the growth rate can stay the same. That's the number of individuals. So here we have the growth rate of the human population in the world. Our population recently reached 7 billion people. So growth rate is predicted to begin to decline around the year 2050 and reach an equilibrium at about 2100. So will that happen? We don't know, but that's a prediction. Okay, so here we have 500 BC. So there's very few people here. And it slowly is growing just a little bit, just a little. Then it grows a little bit more right about 400 AD. Then it drops a little tiny bit, not very much, and then it grows a little. And it goes up, up, up gradually. And then all of a sudden, there's a big decline in the human population. When you look here, that is where Black Death, the disease, killed many, many, many people. And we will learn about that later. So the population drastically went down. Then it started to grow again. And it's growing. And there's about 1500 AD, about 500 years ago. And we keep going. And it gradually increases. And then all of a sudden, right around here, we have a lot of growth. All of a sudden, there's a lot of humans being born and surviving. And what we attribute that to in this area is the Industrial Revolution. In that Industrial Revolution, we made it much easier for people to get food. We were creating food in mass markets, creating machinery that worked better and faster than humans. And so we had a nice boom of the human population. Now, as we keep going, it gets up here, and right around 1980 or so, kablam, it is going up, 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 up. Okay. So we're at 7 billion now. And again, it is believed that about 2050 is when we will reach our equilibrium. So we will talk about that in a little bit. Okay, so let's watch this video. Oop. Sorry about that.
A 1,000 years ago, there were only 1/3 billion people, but we were multiplying. Now there's 7 billion of us. How did we grow so much so fast? Say this glass is North America. The fuller the glass gets, the more people there are. Water drips in as people are born. Water drips out as people die. Okay, here's the entire world. Now let's go back 1,000 years. The Americas are nearly empty. Europe and Africa have less than 100 million people between them. And just like today, most people live in China, India, and the rest of Asia. For centuries, things stay pretty much the same. Births are canceled out by deaths. Women are having lots of babies, but most babies die before they grow up and have families of their own. We don't reach 1 billion until 1804. But things are changing. Better medicine and better agriculture are starting to slow the leak from the bottom of the glass. People still die, of course, but more babies grow up and have babies of their own. Lots of babies. We've grown from 1 billion to 7 billion, and it only took 200 years. Will we keep going like this? Probably not. The UN says we'll level out at 10 billion by the end of the century. So as we continue to grow from 7 billion, the question is, can the world hold that many people? Experts can't agree. It all depends on how well we manage our food, water, and energy.
Okay, so what affects the growth rate? Just like that video just said, the number of births the number of deaths, and the number that enter or leave the population, which we consider to be immigration if the movement is into a population, or emigration if the movement is out of a population. Demography, that's the study of the human population. I bet you've studied some of that in your geography class. So, exponential growth. When we look at this graph, we've got a population size that is growing gradually, and then all of a sudden there's a big boom. That is called exponential growth. Under ideal conditions, with unlimited resources, so meaning they have enough food, they have enough shelter, they have enough clothing, with unlimited resources, that's what a population would happen to look like. The graph to the right is what it looks like, and at first it grows slowly and then it picks up. Now, logistic growth is as resources become less available, so like food, shelter, that sort of thing, the growth of a population will slow or stop. So once it grows, it'll grow slowly and then do the exponential growth, but then it will slow down because if there isn't enough food or shelter or water or space, and it will overshoot at first, and then it will die a little bit, the population, because there isn't enough. And then they realize, oh, we do have enough, so they grow again, and then they die off because they overshoot that carrying capacity. And it keeps waffling back and forth until it kind of levels out a little bit more. So where is the population actually leveling off and reaching carrying capacity on this chart? If you look and you looked at that spot, that is where carrying capacity pretty much has been reached. Okay, limiting factors. These are what causes a population growth to decrease or to slow down. So, limiting factor in this area, it will cause it to go down. So, what is the limiting factor here? Probably water. Okay, so the types of limiting factors are competition between species or amongst the population, predation, parasitism, disease, climate extremes, human disturbances, and natural disasters. Let's watch another video.
My job is to make college easier because students have a lot on their.
Here's a principle of biology. An ecosystem can only support a limited number of species before problems begin happening. So how do scientists determine that number and what things can affect it? Fish and wildlife biologists manage natural resources for the overall health of certain species and the ecosystem where they live. But sometimes a healthy ecosystem gets damaged when too many of a certain species eat all the food. Just imagine a swarm of locusts eating all the vegetation in sight. Once an ecosystem gets that damaged, it can impact the health of everything that lives there. So what's the right balance? Biologists call the right balance the biological carrying capacity. It's the capacity of an ecosystem to carry or support a healthy number of a certain species. For instance, if a forest type supports 2 healthy bears per square mile, what happens if 4 bears try to live there? They may eat all the available food and not find enough to remain healthy. Plus, if they eat all the fruit and nuts, they might damage the next generation of fruit and nut plants in the ecosystem. So So what variables can affect the biological carrying capacity of an ecosystem for a certain species? 1. The abundance of food sources. 2. The sustainability of different food sources. 3. Competition for food from other species. Here's a good example. Sturgeon populations in Lake Winnebago are the highest in the world. So that probably means that the biological carrying capacity is really high considering those 3 variables. A 200-pound sturgeon needs lots of food to go that big. That's a challenge for a toothless fish that simply sucks stuff off the bottom. Fortunately for the sturgeon, that's where they find their 2 prime food sources. Lake fly populations on Lake Winnebago are so immense that they show up on weather radar like a storm cloud during big hatches. These lake flies live most of their life on the bottom of the lake as larvae and pupa, and that's where sturgeons suck them out of the mud. But once they hatch and fly off as adults, they're no longer available as a prime food source. So they're seasonally abundant, but not sustainable as a food source throughout the whole year. However, sturgeon aren't the only fish eating the lake fly larvae during times of plenty. Millions of gizzard shad also eat the insects there. And when the shad go through their annual cycle, many of them die and sink to the bottom, where they provide another rich food source for sturgeon. So combined, the lake flies and shad help provide sustainable or lasting food sources. And that combination boosts the lake's biological carrying capacity for sturgeon. But what if too many sturgeon populated the lake and ate so many lake fly larvae that the flies had trouble reproducing? Or what if another fish species, such as walleye, ate too many of the shad? It's easy to imagine how both of those variables might affect the lake's biological carrying capacity for sturgeon. So how can biologists manage Lake Winnebago for the optimum biological carrying capacity for sturgeon? Like most species of fish and wildlife, biologists help manage an ecosystem by regulating the number of species harvested. If there are too many sturgeon, they can issue more sturgeon licenses to reduce the population. If too many walleye could damage the shad food source, they can increase the catch numbers for walleye. So controlling species populations helps maintain a healthy ecosystem. Now that you know about biological carrying capacity and what affects it, consider studying it for a species near you. It may be something as simple as the fish in your aquarium or robins in your yard. Choose a species that you can observe over time and make a list of variables that might affect the biological carrying capacity for a species.
Okay, so what is the limiting factor in this picture? If you said space, you were right. What is the limiting factor in this picture? If you said war, that is right. What about this picture? What is the limiting factor? If you said a weather-related act or natural disaster, that's it. How about this one? What's the limiting factor? That would be a snake eating a frog. So predation. How about this one? This one's a little tough to know what it is if you haven't seen something like this before. It's like you're looking through a microscope and you're looking at bacteria. That would be disease. And here we have a hurricane from above. The limiting factor would be natural disaster. And then we've got a desert, snow, very, very deep cold here along the right. That limiting factor would be extreme climate. Okay, that's all we have for today. Have a wonderful day.